Assalamu alaikum. So, in continuation to the last lecture where we discussed about the observed survival, today we are going to estimate cumulative surviving abilities for different lengths, time duration. So, in this regard, if we estimate the probability of surviving for first year, we already know that the total number of first year patients who survived were 197 divided by 375 is equal to 0.52, and for the probability of second year survival, P2 is equal to 71. The 71 is actually the number of patients who survived for 2 years, 21, 14, 20, and then we are intentionally saying that they are 71 by omitting this 43, which is encircled over here as green. So this is the P2 probability over there. The denominator is 197 minus 43. So why minus 43? Because this number could not survive for the second year. So this is the probability for second year survival. Now, in order to understand that how many individuals actually survived for on cumulative basis. So for on cumulative basis, how many individuals survived for 2 years? That's the question. So this is the probability of surviving for first year, for second year, third year, fourth year. But on cumulative grounds, that the number of individuals who survived is the same for first year, for 2 years. This is equal to P1 into P2. So P1 is this value, P2 is the given value mentioned over here as 0.461. So we are basically multiplying these two digits together. So P1 into P2 is the value we are retrieving over here is 24.2%. So that's the percentage values mentioned. So that's way we are calculating the values over here. So this is the percentage survival value for this, and I am changing some correction, making some corrections simultaneously. So cumulative value for 5-year survival. So the individuals who survived out of 370 patients for 5 years, the probability is 8.8%. So based on this observation, and this is a hypothetical data of for the patients treated from 2000 to 2004, the graph should be made somewhat like this. I have tried to make it more simplified for you over here. So earlier what we see was like this is the 100% survival. Let me change the color, and this is over here what you are noticing over here on the x-axis is the number of years, how long they actually been able to survive, the years of follow-up. So for example, the year of follow-up over here is equal to 1, 2, 3, 4, and let's say this is the 5 time point. So for 5 years we say that in time point 0 we expect there is 100% survival. Now at time point number 1 the cumulative survival was 52%. So let's say that some at this time point, let's say this is the 50% survival against a particular treatment. So on 1 year survival efficiency was 52. On the second time point, it says, let's say it says 24.2. So we say this is somewhat over, let's assume that this is in the middle way over here. There's the 20 falls over here. That's the 20 point, and it says 24.2. So hypothetically, we are saying the cumulative survival for 52, 24, then we say it's 15%. So if it is 15%, let's assume the values would be around here on the third year time point. Let me put it more in line to the expected time duration value, 13. Then the next fourth value we are observing is 11%. I'm just gauging it to make it more understandable how the survival curves are being drawn. And this says 8.8%. So if we look at the trend line, we say that after giving the treatment, the 1 year survival of these individuals started from here, reduced to 52%. So the patients survived for 1 year, more than half of them, or close to half of them, died. But then there is a second time point, then there is a third time point, and then there is a fourth, and so on. This is the last one, 8.8%. So this is the cumulative survival curve what you are seeing right now. So this is a survival curve of a hypothetical example of the patients who are being started with the treatment 2000 and then followed for 5 years, with two assumptions that we don't have to lose any data. So this is the conclusion of observed survival. And now, in addition to that, we are estimating. Another way to calculate these findings is life table based calculation. So basically this is also, don't get scared of this table. This table is actually in continuation to the previous one. This is basically a notion that over here we assume all the events that there is no loss of follow-up, no loss of follow-up, no loss during follow-up. So we assume that we follow the patients who are enrolled in year 2000 till 2005, and all of the patients remain attached to the study. But this is what you can say, this is a very rare phenomena, and it seldom happens. So one thing we can do is that we assume that there are a certain number of individuals who not only died but also withdraw so during the interval. So how to do those sorts of calculations? The calculations are pretty straightforward. Just look at this calculation. This is a hypothetical way. So suppose that there is a treatment which has been started and is followed for 5 years time interval. So up till 5 years we assume that we are getting this data, and the information of withdrawal individuals is also being provided over here. So we have enrolled 375 individuals. Out of them, after 1 year interval, 1 year time, 178 remain alive, but 0 have withdrawn. So the effective number of exposed individuals died during the interval is not relevant over here. Forget about these blue columns right now. For the next column, second year, during the second year, out of 375, 178 died during the interval, so the remaining value is 197. Okay, so just to make life more easy, 375, and then we are subtracting the number of individuals who unfortunately died, and then the value is 197. So 197 is placed over here. So out of this 197, 83 died during the interval of second year, and 43 withdrew from the study. Okay, so 43 withdrew from the study. So if the 43 individuals withdrawn from the study, the remaining in number of individuals stuck to this point would be 71. Okay, so according to this, and then we are proceeding further for the additional calculations. So we say that 197 individuals, after 197 individuals, 83 died. So this gives us a value of 114, and then out of this 114 value, which should be written over here, we came to know that 43 individuals lost the follow-up, lost during that interval. They may have changed the places, they may opt a different treatment plan, and then we subtract those 43 individuals and we get a true value of 71 individuals. All right, then from 71 individuals, 19 individuals died, and then 16 individuals changed the place of location, or they opt a different treatment, or they may have withdrawn from the study. So the leftover is 336. Similarly, you made this up all these 5 years column. Then now we are interested to know the effective number of exposed risk of dying during that interval. So expected number, effective number of exposed to the risk of dying during that interval. So in order to do that, what we are doing is basically column 2 minus half of column 4, because we assume that half of them may have been actually died during that disease and the rest of the half may remain alive during that period. So we assume that the people who have withdrawn from the study may remain alive half of them, half of a year, and may remain dead for the rest of the time period. We are not, this is just a mean to increase your follow-up retention time. So by doing that, the calculations made were presented over here. The calculations are pretty straightforward. For example, in order to understand how this 175 value came, we can write out the value at column 2, which says 197, and then we are subtracting how much value? 43 divided by 2. Okay, 43 divided by 2, so the value is 21.1%. so if I assume the values, and I'm just writing it down over here, so the value is 21.5, so subtracting it from 197 is giving us 175 value. So we are just rounding it off to 175 value presented over here. So the number of individuals who have an effective risk of dying during this course of 2 years is 175. All right, and so on the column goes till 13. Next thing is to calculate the proportion who died during this interval. So in order to calculate a proportion, the calculation is given over here in a very simplistic form, and the simplistic way of writing this proportion value is mentioned over here as column 3, number of individuals who died. For example, over here the number of individuals who died in column 2, I am intentionally sticking to column 2 so that you can make it more understandable for you. So let's say the number of individuals who died, and we are calculating the proportion. So 83 individuals who died during that period, and then we are getting back to this risk, and then we are saying that half of them for the denominator value. For the denominator value is given over here is as 175. Okay, so when we do this, we are getting a proportion, and the proportion value is mentioned as follows: 0.47. Alright, so this value I have mentioned over here. Now this story goes on. Just to double check, for example, if I want to do for 3 years, the value pattern would be 19 divided by 63. 19 divided by 63. So the value is equal to 0.30. You can add 302 or whatever you want. Then the proportion of people who died is calculated over here. But since we are calculating a survival analysis, so what we do subtract this proportion from 1. So the value of proportion calculated over here is being subtracted over here. So 1 minus 0.47 is giving us a value that is, let's me write over here, that's the value we are getting, 0.25. That's the value over here. Similarly, the next point over here is also the values obtained over here, the 5.52, 0.68, 0.76 and 0.84. Now this is the proportion of people who did not die during the interval of first year, and this is the proportion of individuals who doesn't die for the second year. But as we have stated earlier, for cumulative probability values, as we have mentioned over here, we do a multiplication for these observations. What we do for cumulative proportion of individuals who survived from enrollment to the end, what we are basically doing a cumulation over here, that is 0.52, that is 0.52 into 0.527, and then the value is given over here. So we are doing the same stuff we are doing. Let me write somewhere over here is small m, so you can understand that the multiplication step is going on in this phase. So what we are doing, we are multiplying P1, which we obtained over here, with P2 over here. So the value is written in this regard as mentioned over here. Alright, so this is a cumulative multiplication. So how we obtain 0.193 It is basically multiplying P1, P2 and P3. Or in simple words, we just multiply zero point 0.2 with 0.698 and we get the value of P is equal to 0.193. So how we are doing it? This is just by multiplying this value with the number presented over here. So this is giving us a cumulative proportion value of the number of individuals who survived for 5 years. And similarly, towards the end, last thing, if we want to draw a graph somewhat for a survival of individuals and with an assumption that certain number of individuals have lost contact, we are making a year age over here 0, 1, 1, 2, 3, 4 and 5. And for lifetime calculation, the difference between this table and the prior one is that over here we assume that all the study cohort participants stayed with us during the course of the disease, but in reality it doesn't happen. Sometimes people do withdraw from the study cohort. So in that case the calculations are presented over here, and in this regard the values would be also be converted into percentage, and then the percentage values of, let's say, 52% and the rest would be mentioned accordingly in the survival curve. Okay, so just this is just an alternate method of presenting the findings. So over here what we are getting is 52%, 27% survival, and for 3 years the survival says 19% value, 14% value and 12%. So this is just the main observations we have recorded. For 100% for 1 year the cumulative survival value stays to 52%. Let's say this is the 50% bar, and from 50% let's say this is 25% survival. For the second year survival rate exceeds over here, some way fall over here, this time point, and from this time point if we extend it the times to different arbitrary values given as 19, 14 and then 12%. So never close to it is close to 0, but it never touches this x-axis bar. All right, so this is how you draw a survival analysis curve for observed lifetime table calculations. So far, there are three means we have discussed regarding prognosis. Number one, observed lifetime table. We talked about case fertility rate. Then we talked about the survival, and in the survival, we talked about observed survival and lifetime survival. Now, the third important parameter is about the Kaplan-Meier method. Most of you may have heard about the survival analysis in what you can say. Majority of the cancer research work is focusing on Kaplan-Meier survival curves. So what is a Kaplan-Meier survival curve and how we do this survival analysis, that is being discussed over here in a very simple and elaborative form. So basically there is, and the Kaplan-Meier survival curve works on two things. That is, there is no predetermined interval as 1 month or 1 year to be used. Likewise, as you have stated over here, 1 year, second, third, fourth and fifth year. Basically, Kaplan-Meier is an event-based survival curve which is being drawn, and the exact point of time when the death occurs which leads to the interval break and initiation of a new interval. So since it is not using a regular interval time frame of 1 month or year as we have noticed over here, it is what it is doing? It is doing the time points where the death or an event has occurred. Why we have mentioned an event or death? Because in certain cases the Kaplan survival curve doesn't deal solely with the death reports. It may also be dealing with certain other parameters like age or other influencing factors. So it is an event-based Kaplan-Meier method, and over here let's assume the example of 6 patients which are being followed for survival, and to draw their time duration let's assume that there are 6 patients which are being followed for 24 months, and then these 24 months duration is being elaborated over here because the 24-month time the last patient has also died over here. I have intentionally left it blank so that you can get an idea. the number of individuals are enrolled in the study and they are followed for 24 months. The first patient died at this 4 months of duration. Then there is a patient who died at 10th month of the study. This third individual died at the 14th month of the study, and the last one died or expired at 24th month. Okay, then there are two individuals who have been lost during the follow-up time period. Okay, so in this case each event is actually a separate identity. So the graphs, your stepwise initiation factor would be noted over here. So the pattern of line of survival curve would be somewhat like this. Okay, so that is how it is different from the survival curve what we are noticing over here. Okay, so based on an event base, you can see a staircase pattern over here for the survival. That's the simplest thing right now you need to understand. Because it is an event bound study, any event is going to set as a time point. 4 months is the time at which the first patient expired, then 10, 14, and so on. Now, how to make a table for Kaplan-Meier survival? For Kaplan-Meier survival, the time stated over here is mentioned as the time to the death from the starting of the treatment is 4, 10, 14, and 24. 4, 10, 14 to 24. Number alive at each time. Now here comes the interesting fact. Although the patient died at 4th month, but for numerator value, we are calculating all the number of patients enrolled and alive at that time point. So let's say the patient was alive till 4th month of the study. So we count all these patients from patient 1 to 6. That's why we wrote 6 over here instead of 5. The number who died at each time. So there is one death which has been reported in the 4th month. It could be the first day, it could be the last day, or it could be 15th, the midpoint. So we are assuming all the patients were alive at till 4th of the month, and then one patient died. The proportion of individual who died at time is the proportion calculation done is the simplest way by dividing 1 by 6. So pretty straightforward. 1 by 6 division gives us 0.167. Now the proportion who survived at time, because we are talking about the survival, so the values we are using is pretty straightforward. 1 minus column 4 value is equal to 0.833. And again, for the same trend of cumulative proportion who survived, we are multiplying this number with this one so that we can get 2 years survival. Okay, so 0.83, 0.62, and then 0.62 multiplied by 0.66 is giving us a value of 0.417. And similarly, if we multiply this number with this value, the values we are getting are mentioned over here. I am just intentionally mentioning these arrows and pointers so that you can get an understanding how this table has been drawn. The table you have was actually retain the information all like this, and the remaining values are being incorporated from your side over here, and we are intentionally avoiding those individuals who are lost to follow up at this stage. Lost to follow up have been avoided for the Kaplan-Meier survival. So in order to assess a time scale or close to the time scale Kaplan-Meier survival, let's say the same graph has been drawn over here. Since the time point says 4 months, 10 months if I'm remembering correctly, then there is a 14-month slab, and then there is a 24 month. So we say that on time 0 there are 100 individuals and there are all of them are surviving. Then at 4 months there is an event over here, and this event says, since there is an event, so there is a drop. How much is the drop? The drop is about 83%. Sorry, I have drawn too much out of the scale, so let's keep it close to our predicted values. Let's say that 100% is over here and we assume the 50% values falls over here. So from the first death, the values are mentioned over here is given as follows. Then in the subsequent time duration, there is a 62% loss. Okay, so again, this event says 83%. Let's say this is 83%, and then we assume that this time point says the value. From here, I am getting 83, 62, 41, and 0. So I'm writing 62% over here. Then from the third event, which was happening over here, the value ranged from 41%. So let's say the 41% value is mentioned somewhat closer. So let's say it's 41%, and then lastly the individual has just expired at the 24th month, so this value says zero point 0. Okay, so this is basically a Kaplan-Meier survival curve that is drawn after the months of enrollment. So this is an actual real ground data which is based on two things: that nothing has been happening on temporal level and the therapy hasn't improved over a period of time, which is not obviously a true thing. Therapies do improve during a certain time course. So we assume that there is no temporal involvement, that the people doesn't improve with the passage of time, and the reason of death is solely because of the treatment they are getting. What I mean to say that the patient who died over here in this stage is solely because of a cancer complexity, not of the COVID influence. I mean, not any tertiary factor is responsible for the death of these individuals. So there is no temporal change which is influencing this factor. This is the assumption number one. Number two assumption says that there is no improvement in therapy has been done so over the past. These two assumptions are quite, what you can say, fictitious in their terms, because people will be influenced by these 2 years by numerous other factors. All right. So in order to assess those factors, the for prognosis, there is a fourth time which has been incorporated, and this value is just for the sake of your understanding. We are not extending it any further from here onwards, but it is generally called, instead of getting mean values, instead of seeking mean values for in these terms, why not, if we have a chance, we can focus on median values, and we can focus on median survival time. Okay, so that median survival time. So the reason of adding median survival time is that in case there is a mean value we are calculating somewhere, the mean values may dislodge us from the extreme means. So the median value is the more accurate measure for survival analysis. So this is just another way of presenting our findings. And last thing, in addition to Kaplan-Meier survival, says relative survival. Relative survival is basically an indication that if we are doing some assessment, we should be comparing two things together, because if we want to understand the treatment response, we should be comparing that treatment with any other additional factor. That if we say that the treatment 1 has an advantage of increased survival, let's say this is treatment 1 and this treatment has an advantage. Let me change this color with another one. So this is treatment A and this is the treatment B, and let's say we are assuming that we are dealing with the patients of let's say HIV infection, and we say that the number of individuals treated during a 5-year course from 0 to, let's say, 1, 2, 3 and 4, and during this course of 5 years there should be a relationship that whether treatment B has a good survival or treatment A has a good survival. In terms of a mathematician perspective, we would say that both the lines red and blue coincide at this time point of, let's say, at this fourth point of the year. Okay, but at this time point, both these treatments are alike. But from a gross assessment, you could easily say that the number of individuals who were given treatment A remained alive more, remained more alive for 3 consecutive years, right? So we will prefer this treatment over treatment B. Why? Because the number of individuals who were given treatment B, there is an abrupt decrease survival, as we have noticed, from 100 to, let's say, less than 50, somewhere over here. And then the second year there is also the death events reported, and then the third year. Although the survival analysis at the terminal point coincides among both these groups, treatment A and B, but we are preferring a relative survival time, and based on this relative survival time, we assume that treatment A has a preferential advantage for HIV treatment as compared to treatment B, right? So this is how we learned about the severity of a disease, and this is how we can gauge the prognosis of a disease. So there are 5 tools which have been discussed over here. The tools are mentioned. So case fatality, then observed 5-year survival, lifetime table calculation, and Kaplan-Meier survival. Then Kaplan-Meier survival followed by median survival, and median survival is just an alternate mean. Instead of switching to the mean, you can go for a median value. This is just enough for you right now for an understanding. And fifth one is basically for a 5-year survival, you do a relative assessment and compare the treatment A with treatment B and assess which one has a preferential advantage over the other. Okay, thank you very much for your time and attention. If you have any questions, please feel free to ask. Thank you.